Hello, very good day. My name is Carlos Lopez, and this is Keynote 4.4 on co-treatment of fecal sludge in municipal wastewater treatment plants as part of the online course on fecal sludge management. I'm Carlos Lopez from UNESCO ISG, and I am Associate Professor on Wastewater Treatment Technology or Sanitary Engineering. What's the problem with fecal sludge management? Well, usually one of the main problems or practices is that there is a lack of proper planning of the fecal sludge management. Another problem is that if we consider that there is a lack of planning and that there are 1,000 tons of fecal sludge that need to be collected, transported, treated, and disposed of in a safe manner, then we can immediately realize that there is a big issue to deal with these residues or these elements generated in the system. So some of the major challenges of fecal sludge are how to do the emptying of the pits, of the vaults, of the septic tanks, how to transport these residues in a safe, adequate, and efficient way, and the most important for this unit is how to treat them and how to have a safe disposal or reuse of this fecal sludge. So the main learning objective of this unit is that after the completion of this online lecture, the reader, the student, or the participant will be able to evaluate and propose or to have key considerations to co-treat the fecal sludge in municipal wastewater treatment systems, if feasible. To start with, I would like to talk about the fecal sludge characteristics. Because even if we try to put or categorize the fecal sludge in two main treatment or in two main categories, for example, public toilet or septic tank sludge, we will find that they have quite variable and different characteristics. For example, if we talk about the total solids content that we can find in public toilets, that is supposed to be fecal sludge fresher, more freshly generated in the systems. Again, septic tanks where the sludge, the fecal sludge has been already exposed to certain for certain time to certain storage conditions or certain digestion processes, we'll find the total solids content will vary widely. For example, public toilet can go from 30 to even 52,000 milligrams per liter, and for septic tanks can also range from 12,000 to more than 35,000 milligrams per liter of total solids. Looking at other parameters, like for example the content of volatile solids, there is also quite a broad range of characteristics of volatile solids, from 65 to 68%, or even 73%, 50% for septic tank. We look at, for example, how to measure the organic content based on CUD or in BUD5. The ranges are also quite broad, from 10,000 to 250,000 milligrams of CUD per liter for public toilet that is fresher, that has not been digested, but still 10,000 to 250,000, that's a broad range. For septic tank, from 1,000 to more than 90,000 is also quite variable. Looking at other parameters like the BUD5 that provides certain information about how biodegradable can be these organics, we can find that, well, based on the limited literature, a bit more than 7,000 milligrams per liter can be measured as BUD5 of all the organics present in that fresh public toilet sludge. While for septic tank, also varies widely, reaching up to 30,000 milligrams per liter of BUD5 in that system. Looking at some other compounds, like for example nitrogen or phosphorus, we can find similar trends with total nitrogen, for example, for septic tank, reaching more than 1,000 milligrams per liter, 1,000 as total Kelder nitrogen, considering that total Kelder nitrogen involves not only the organic nitrogen, but also the inorganic nitrogen present in the wastewater, or in this case in the fecal sludge, and that ammonium ranges for public toilet from 2,000 to 5,000 milligrams per liter, and septic tank a bit more than 1,000 milligrams per liter. While for total phosphorus, we can see public toilets concentrations of more than 400 milligrams per liter, and for septic tank up to 300 milligrams per liter. So overall, the characteristics of the fecal sludge, either proceeding from public toilets or from septic tanks, is quite diverse or quite variable. This led to the need to categorize these fecal sludge in a more narrow ranges to try to understand more about how this fecal sludge can be treated or can be disposed of in a better way. And based on the information available in literature, we were able to characterize them or to categorize them in three main categories based on the strength of the fecal sludge. For example, high strength for the really upper part of sludges found in the literature, medium strength for medium values, and low strength for the lower values reported in the different reports, and trying to categorize them also based on whether they were fresh or digested. It could be possible to find 6 different categories: high strength, fresh, high strength, digested, medium strength, fresh, and digested, and also low strength, fresh, and digested. That can provide some further information about how these different sludges are generated in the different fecal sludge collection systems. However, that does not provide enough information about how these different sludges can be treated. For that, we have focused, or we have considered, some principles or some other fundamentals developed in wastewater treatment systems. For example, in wastewater treatment, it has been possible, based on different research developed in the last 25 years, come up with a fractionation of the organics present in the wastewater based on the biodegradability of these organics, but also attending at how these organics can be present in the system, either in a suspended or particulate way, or in a soluble or more dissolved nature. Because depending on these characteristics, it is possible to define or determine whether these different organics can be removed or not, and how they will be removed in the different wastewater treatment systems. For example, for fresh and for digested fecal sludge, it is possible to estimate the biodegradable fractions and also the non-degradable or unbiodegradable fractions present in those two sludges. That also gives or provides information about how much is the amount that we can really degrade biologically from that fresh fecal sludge or from that digested fecal sludge. That is about a bit more than 40% or 0.43 parts of all the COD present in the fecal sludge that is really biodegradable, and almost 20% or 0.19 of all the organics present in digested fecal sludge. This already provides to us some information about what can be really biodegraded in treatment systems of those sludges. That also implies or provides to us information, important information to understand that the unbiodegradable fractions present in the fresh fecal sludge can reach about or almost 60% of the total organics and about 80% of the total organics. So basically, this already can give us enough information to understand that the fraction that cannot be biodegraded by biological means from those sludges is or comprise most of the total organics in our sludges. looking at, or into more detail, at the different fractions, but now considering whether they are particulate or suspended. That means fractions that are more complex, that are not dissolved, that need to have or to undergo a certain hydrolysis and fermentation, and parts that are soluble, or in this case soluble, that are smaller particles. We can use these two concepts to combine them with the biodegradable or unbiodegradable nature of those compounds and get more information about how and in which way these fractions of organics can be removed in an activated sludge or in any other wastewater treatment system. For example, here we have two particulate or two suspended fractions. The ones that are non-degradable or unbiodegradable, and the ones that are degradable. The degradable fractions in fresh and digested sludge are of about 0.31 and 0.15 respectively, while the unbiodegradable particulate fractions comprise most of the organics present in fresh fecal sludge, almost 50%, and almost 70% or 0.70 in digested fecal sludge. What also provides to us, or gives us also the impression that most of the organics present in the sludge are non-degradable and also particulate. Basically, particulate organics, solids that are being transported or are present in this sludge. If we look at the soluble fractions, either biodegradable or non-degradable, we can see that those comprise just a minimum part of all the organics present in the fecal sludge, about 0.15 for the case of fresh sludge and 0.04 for digested, while the soluble non-degradable 0.09 and 0.12. What does it imply? Well, if they are soluble, that implies that they cannot be removed by physical means because they are soluble or dissolved in the water. Nevertheless, if they are biodegradable, they can be utilized or used by the biomass to produce more biomass and therefore being degraded in the system, being removed from that waste or that wastewater or that fecal sludge. While the parts that are soluble and non-degradable, that's 0.09 and 0.12, so about 10% of all the organics, they are soluble, so they cannot be removed by physical means, but also they are non-degradable, so they will basically be present in the water and not be removed in any biological waste water treatment system within the boundaries where most of the treatment systems operate. This also implies that these biodegradable fractions, either soluble or particulate, may be able to be removed in the plants if they are subject to the required operating conditions that biological systems need, being able to be removed by the microorganisms. However, this particulate fraction that is not degradable will not be able to be removed and will mostly accumulate in the system because it cannot be used by the organisms, but it will accumulate since it is suspended and particulate in the system. While this one that is a soluble, unbiodegradable, will basically just float, get dissolved in the system, and leave through the effluent, having the strongest impact in our effluent quality. So basically, based on the previous information about the COD fractionation and the characteristics, we can now get some hints about what the composition of the fecal sludge is and how those components or those elements of organic origin can be removed. But basically, what we can see is that most of them are particulate, non-degradable, so not being able to be removed biologically and only accumulate, and a big portion is soluble, unbiodegradable, having a strong impact in our wastewater treatment plant efficiency. If we look at the fractionation of the nitrogenous compounds, following a similar process or a similar approach, we can write down, for example, the fractions that are composed by free and saline ammonia, the fractions that are composed by organic, non-degradable, or in this case, unbiodegradable particulate nitrogen, and the parts that are present as unbiodegradable soluble nitrogen. These compounds will have or will behave in a similar manner like the organics, being free and saline ammonia available by microorganisms, either to be oxidized or to be used as part of the nitrogen requirements, or in this case, biodegradable, soluble, or particulate that, since they are not degradable, will either accumulate also in the system or will flow out or flow through the system without being removed. How are these fractions in fecal sludge? Well, basically, we can see that in fresh fecal sludge, most of the nitrogen is free and saline ammonia, about 84%. That means that this fraction in this fresh fecal sludge will be able to be oxidized or used by the microorganisms, so we can remove this fraction. However, the other two fractions that are about 15%, 0.01 organic unbiodegradable and 0.15 organic unbiodegradable soluble, will not be able to be removed, one getting accumulated in the system, the particulate one, and another one being or flowing out of the system, the soluble one. When we look at the digested, and because most of the sludge has been already exposed to certain digestion, either in the septic tanks or in any other fecal sludge collecting system, we will see that the range has changed, interestingly, being now the free and saline ammonia about 0.20 or 20% of the total nitrogen, 5% the organic unbiodegradable particulate, and about 75% the unbiodegradable soluble nitrogen. What are the practical implications of this? Well, basically, these that is soluble, unbiodegradable, cannot be removed biologically, and it is soluble, so it cannot be removed physically, and it will have, therefore, the strongest impact in our effluent. In a similar way, like the particulate non-biodegradable, the organic unbiodegradable particulate nitrogen will also tend to accumulate in our system and will be mostly solids that will start to build up in our wastewater treatment plant. So this COD fractionation, when it gets combined with the characteristics of the fecal sludge, can already provide to us enough information to understand and get some important information to assess or foresee how these compounds will not only be able to affect our plant, but also how they could be removed. Those implications can range from, directly speaking, the very high COD and total nitrogen loads that will need to be treated, higher total suspended solids that will be generated in the plant because of these very high organic and nitrogen components present in the fecal sludge. This could lead to aeration limitations because most of the wastewater treatment systems, for example, the aerobic treatment systems, will have problems to cope with the much higher total suspended solids concentrations, what is going to have a strong impact on the oxygen transfer efficiency that will decrease the amount of oxygen that we can transfer from the oxygen supply systems to the bulk liquid, and also because there is less oxygen that we can transfer from the supply system to the microorganisms for them to degrade the organics, there will be the problem that will be a higher oxygen demand to compensate for that drop in oxygen transfer efficiency. There will be some pH issues, possibly, because if ammonia gets oxidized, ammonia, or free and saline ammonia, it will consume about 1 milligram of alkalinity per every milligram of free and saline ammonia that is oxidized. And if alkalinity is limited, or in other words, if there is not enough alkalinity supplied to be able to oxidize all the free and cellular ammonia, very likely the pH will drop, and a drop in pH below 6.5 or 6 will inhibit not only the aerobic processes, but maybe the whole plant. Another problem of these characteristics, as you could foresee, is that the very high content of soluble unbiodegradable compounds that cannot be removed neither biologically nor by physical means, will have a very strong impact on the effluent quality. That, for example, in the case of the European Union Water Framework Directive, establishes a total chemical oxygen demand of about 125 milligrams per liter, 10 milligrams per liter of total nitrogen, 35 milligrams of total suspended solids, and 2 milligrams per liter of total phosphorus. Standards that will be difficult to meet when discharging big fractions or portions of fecal sludge into an existing wastewater treatment plant. And last but not least, because of the high accumulation of suspended solids, the likelihood to have secondary settling tanks or primary settling tanks overloaded with solids is very high. And that risk may lead to the total deterioration of the activated sludge plant. In the coming slides, we're going to look at one example that will be used to exemplify and to show in a more quantitative way how these components or how these characteristics affect, in this case, an aerobic wastewater treatment plant, an activated sludge plant. And so, to exemplify this, here we have one activated sludge system. This activated sludge system has configuration composed of an anaerobic tank, followed by one anoxic tank, and one aerobic tank. Basically, the typical configuration used for nitrogen and phosphorus removal in an activated sludge system. Besides the aerobic, the anoxic, and the anaerobic tank, it also contains one secondary settling tank that is an important component in all activated sludge systems. How does it work? Well, basically the influent is discharged in the anaerobic tank, mostly for or to enhance the biological phosphorus removal processes, flows to the anoxic tank where denitrification processes take place for nitrogen removal. For that, it is necessary to have a recirculation from the aerobic to the anoxic stage. And then we have the main tank, that is the aerobic tank, where the organics, the nitrogen, are oxidized and removed in this system. Once the organics, the carbon, the nitrogen compounds, and the phosphorus are removed by the microorganisms, leading to the growth of more organisms, the organisms or the biomass is settled in a secondary settling tank to have a treated effluent that will flow clean, treated out of the wastewater treatment plant. And most of the solids accumulated at the bottom will be recirculated back to the system to always ensure that we have enough microorganisms, enough bacteria for us to continue removing the organics and the nitrogen and the other compounds, and discharge excess of solids that we don't need to be able to give a desired operating conditions. For this example, we consider that this is a plant that is treating about 20,000 cubic meters per day of wastewater, so it could be considered like a medium-sized wastewater treatment plant for about 100,000 people equivalent. Works at a standard temperature of 20 Celsius degrees with a solid retention time of 10 days. That means the average time that the solids will spend in the system is 10 days, with a total suspended solids concentration of 4.5 grams per liter distributed in the whole system. Treating 750 milligrams of COD per liter as a measure of the organics being discharged into the wastewater treatment plant, containing also 60 milligrams per liter of nitrogen, as total nitrogen, 15 milligrams per liter of total phosphorus, and 400 milligrams of total suspended solids per liter. This is our model wastewater treatment plant that was modeled in BioWin. And what we do after this plant is being optimized for the removal of these components is to start to discharge fecal sludge. How much fecal sludge? Well, basically we have considered certain percent of fecal sludge on a volume basis with regard to the influent flow rate treated in the wastewater treatment plant. Well, we are discharging from nothing, that is our baseline, basically when there is no fecal sludge discharge, up to 10% fecal sludge to the plant. That implies that, for example, for about 1%, we are discharging about 20 cubic meters of fecal sludge on a daily basis. That is equivalent approximately to about 40 tanks with a volume of 5 cubic meters, or 25 tankers with a volume of about 8 cubic meters per day. And believe me, this is a pretty fair and common case found in several plants around the world where fecal sludge is treated or co-treated in activated sludge systems. Okay, but we expanded the discharge up to 10% of the total flow rate treated in that plant. What is going to happen? Well, as you can imagine, as soon as we start to discharge the fecal sludge as a function of the wastewater treatment plant or the wastewater treated, we will see that the total CO2 in the plant will start to increase linearly. This is a bit an overestimation, just to show what can happen if we discharge, for example, high strength fresh fecal sludge, and if it reaches 10%, it will be potentially reaching more than 20,000 milligrams per liter of CO2. This is really an extreme case. But we can see that already with 2 or 4%, the amount of organics that need to be treated will reach easily more than 4,000 or 5,000 milligrams per liter of CO2, a considerably higher amount of organics that need to be treated. And there is a similar trend observed if we look at the total nitrogen discharged in the influent of the wastewater treatment plant. For similar values, from 75 milligrams per liter of total nitrogen that we were removing in the plant before the discharge of fecal sludge, now very easily we will reach up to 150, almost 200 milligrams per liter of total nitrogen if fecal sludge starts to be discharged into the plant. So almost double or more than double the concentration originally treated. And in a similar way, the suspended solids concentration in the influent will increase, affecting also our wastewater treatment plant, already with very limited or low volumes of fecal sludge discharged. What are the implications of the discharge? Well, basically, all these organic loads, nitrogen loads, solids loads, will have a direct implication in the biomass. Of course, we have noticed that a big portion is not degraded. But there is also another portion that is biodegraded. That portion that is biodegraded, if it can be able to remain in the system during the operation of the plant, will lead to the accumulation of solids. Those solids can be of organic origin or inorganic origin. Those elements that proceed from the organic origin will be basically the new biomass of ordinary heterotrophic organisms that will grow on the biodegradable organics present in the wastewater and in the fecal sludge, creating certain active biomass, certain organisms that are removing the organics. The decay or the decay of those organics will lead to the accumulation of some endogenous residue that is being built up from the endogenous residue, the endogenous processes of those bacteria when they are dying or being exposed to endogenous conditions. But there will be also the accumulation of that unbiodegradable particulate organics that we notice can go up to 70% in fecal sludge in the system. And this will build or will accumulate in a wastewater treatment plant. So if we apply or determine these masses, we will be able to know and determine what is going to be the increase in solids in our activated sludge plant if fecal sludge is treated. How to do that? Well, for wastewater, and based on the mathematical model developed by the University of Cape Town, the group of Professor George Ekema, applying that model, it can be possible to determine the masses of the active biomass, endogenous residue, unbiodegradable particulate organics accumulated in the system, and the amount of inorganic suspended solids also accumulated in that system. These components, based on the steady-state model from the University of Cape Town, can be determined based on the yield of the organisms, the flow rate, the concentration of biodegradable organics, both soluble and particulate, the applied SRT of the system, and they are reciprocal to the endogenous processes of that biomass, also the SRT. And the endogenous residue can be quantified based on that mass of active biomass present, but also affected by the endogenous processes, the amount of endogenous residue generated from those endogenous processes, and the SRT applied. While the particulate unbiodegradable organics present in that system can be estimated based on the flow rate, the concentration of particulate unbiodegradable organics present in the influent of the plant, times the SRT, and divided by a conversion factor that takes into account the equivalent in VSS, in volatile suspended solids, of those organics. While the inorganic suspended solids can be estimated based on the flow rate, the concentration of inorganic suspended solids present in that influent, and the SRT applied. All these equations can be found for further reading in the book of Biological Wastewater Treatment, Principles, Modeling and Design, edited by the International Water Association. For the sake of this presentation, basically we have worked out these expressions and expanded to take also into account the concentration of fecal sludge that can be usually observed. For that purpose, we add or we use a similar expression, but now instead of considering the total flow rate discharged in the plant, we consider the volume of fecal sludge treated, the concentration of biodegradable organics present in that fecal sludge, and the same expression can be applied to estimate roughly the active biomass fraction that will be generated in the system due to the biodegradation of the organics that can be degraded biologically in that system present in the fecal sludge. In a similar way, the endogenous residue can be quantified using the same equation, but now, instead of considering the active biomass fraction of the system, we can use the active biomass fraction generated from the fecal sludge, and we can also take into account the amount of unbiodegradable particulate organics present in the fecal sludge, together with the concentration of the organic suspended solids that is also calculated in a similar way like for the wastewater, but with the components or the concentrations present in the fecal sludge, it's possible to estimate the new mass of solids that will build up in the activated sludge plant because of the discharge of the fecal sludge. If we estimate now what's going to be the concentration of total suspended solids based on the addition of the fecal sludge as a percentage of the volume of wastewater treated in the plant. We plotted in terms or function of whether the sludge is fecal sludge, fresh, digested, of high, medium, or low strength. We can estimate the minimum concentrations. And it can be seen that already with concentrations of about 2%, the increase in solids concentration can reach up to 40 kilograms of total suspended solids per cubic meter. Whereas the wastewater treatment plant will hardly be able to handle more than 5 or 6 kilograms of total suspended solids per cubic meter. No need to mention what's going to happen if we treat more fecal sludge in that plant. That will cause, because of the accumulation of solids, that will immediately cause a considerable increase in the sludge production. There will be more solids being accumulated in the plant, not only because of that degradation, but also because of that accumulation of particulate organics. We are only moving solids from one point, and we are adding those solids into the system. How much solids? Remember, up to 70% in the case of digested sludge, and about 50% in the case of fresh sludge. These solids will need to be removed from the plant, and already with 2% fecal sludge discharge, we will have up to 1,000% increase in the original amount of fecal activated sludge discharged or removed from the plant before fecal sludge was being treated or co-treated. That means that the amount of solids that we will be taking out are going to be considerable. And this not only implies the need to have the required equipment, pumps, to extract the sludge, but this also implies that we need to have in place the required sludge handling facilities to deal with this sludge. Remember, the sludge cannot be disposed straightforward. It needs to be, for example, dewatered. It needs to be composted. It needs to follow different processes to reduce the volumes, to reduce the aggressivity of these sludges. And for that, the cytostream processes are rather important. And if we are increasing in such a big amount, the total amount of solids generated, it's possible that our sludge handling facilities will not be able to cope with this tremendous increase in the amount of solids that are being produced. On top of that, we are going to have some aeration limitations. Why? Because first, we were treating certain amount of organics, certain amount of nitrogen in the system that can be estimated with this equation that takes into account the biomass yield on COD basis, flow rate, the amount of biodegradable organics present in our system, the endogenous processes of the bacteria based on the biomass, active biomass, endogenous processes, the fraction of endogenous residue generated, and the conversion from that endogenous residue into COD units, plus the amount that is needed for nitrification. Basically, the influent flow rate times the concentration of free and saline ammonia, and the 4.57 milligrams of oxygen needed to oxidize every milligram of ammonia. These are the oxygen requirements before fecal sludge is treated. But if in addition to this, we also consider what are going to be the oxygen requirements to treat and remove the biodegradable organics present in the fecal sludge, as well as the nitrogen components present in the fecal sludge, we can expand the total oxygen demand of that plant co-treating wastewater and fecal sludge with these two expressions. And that will tell us or give us an estimation of the total oxygen requirements of the plant. And these oxygen requirements will increase linearly as a function of the percent of fecal sludge of different nature discharged in the plant. But for example, it can be seen that even for the lowest strength digested fecal sludge, there is a considerable increase in the total oxygen uptake rate of the system, already with 4-6% discharge of fecal sludge. No need to mention what's going to happen when the sludge is more concentrated. We'll have a tremendous increase that will increase linearly, and with less than 1%, it will increase in more than 50% the total oxygen requirements of our plant. Why do we need, or why do we reach these maximum values? Well, because in most of the cases, the system will have certain capacity to transfer the oxygen, and if we start to discharge more than the amount that we can be treated, we will reach certain maximum transfer capacity. Why is this happening? Well, basically, because it has been reported in different research studies that the total amount of oxygen that can be transferred to the water from an oxygen supply system to the bulk liquid is function or depends on the amount of total suspended solids present in the aeration tank. If we have no solids or is very low, we'll have the maximum oxygen transfer capacity. But the more solids we have in the system, the less or the lower the oxygen transfer capacity, usually expressed or measured in terms of the alpha factor. So for a system with a very little concentration of solids, for example, up to 5 grams per liter, that is also equivalent to 5 kilograms of total suspended solids per cubic meter, we have an oxygen transfer efficiency of more than 80%. However, if we start to increase the amount of solids, or if there is an accumulation, a higher accumulation of solids, that transfer capacity will drop considerably, and already at around 10 grams per liter, the capacity will be of about 50%. And if we continue to increase it, we'll reach very, very low values already at 20, 25 grams per liter, 20, 25 kilograms of total suspended solids per cubic meter. A complete or a big decrease in capacity. Combining this decrease together with the increase in solids concentration that we could experience in the activated sludge systems when fecal sludge is discharged, it will be possible to see that the relative decrease in the alpha factor will be dramatically lowered as the percent of fecal sludge concentrated in the plant increases, reaching values as low as 20% already when 2% or even 1% of the fecal sludge is treated. For the two lowest or less concentrated sludges, already a 70-80% discharge, or drop in aeration efficiency can be observed. What are the implications of these processes? Well, the implications is that we will need to double or increase dramatically the aeration in our system to compensate for that drop in the aeration efficiency, in the oxygen transfer efficiency of our plant. That means that to compensate, we will need to increase dramatically our aeration capacity and even double it already with 1% and increase even further as the fecal sludge increases in our plant. So if we don't have enough aeration capacity in the activated sludge plant, it's very likely that the oxygen will drop. If the oxygen drops and being the system and strictly, or some processes strictly aerobic, a drop in oxygen, particularly below 1.5 milligrams per liter, can possibly lead to an incomplete oxidation of the organics because there will not be enough oxygen for the bacteria to continue with the degradation of the organic compounds. It will lead to the inhibition of nitrification, because nitrifiers will not be able to find or to have enough oxygen to continue with the oxidation of ammonia. And that can also lead to filamentous bulking sludge. Bacteria that grow in a bulky way, like filaments or hairy shape, that will make the flux, or in this case the sludge, fluffier, more bulky, and it will not be able to settle down in the secondary settling tank. And if it cannot settle down, and if it loses or it gets lost or reaches the effluent, that will immediately or directly affect the quality of our treated effluent. And on the other hand, if it doesn't reach enough compaction in the bottom of the secondary settling tank, there will not be the possibility to recycle enough amount back to the activated sludge plant to keep the desired concentration of organisms in the system. So overall, these conditions, a drop in oxygen concentration, can lead to a complete deterioration of the wastewater treatment plant. And there is a correlation found between the TSS and the dissolved oxygen. So we can see that the more fecal sludge we treat, already 5% fecal sludge, if we reach 5 kilograms of total suspension per cubic meter, our dissolved oxygen will, in some cases, already reach 0.6 milligrams per liter of dissolved oxygen. And in some cases can go even below 0.2 milligrams per liter with 10 kilograms of TSS per cubic meter. So already at the very low concentrations of or discharge fractions of fecal sludge, the system may start to have limitations regarding the oxygen concentration that can be kept in the aerobic system. Another issue that we have discussed is the pH. Because of the very high concentrations of nitrogen found in fecal sludge, there is a big risk that if there is not enough alkalinity, the pH will drop. And it can drop because 1 milligram of free and saline ammonia consumes 7.14 milligrams of alkalinity per in the system. If the alkalinity drops below 100 or 50 milligrams per liter, the pH in the mixed liquor will very likely drop below 7 or approach 6 in that system. And what are the implications? If that happens, the problem is that particularly for nitrification, for example, the optimal pH range can be found between 7 and 8. Being nitrification highly sensitive to a pH drop, already if the pH reaches 6.5, we'll have about 60% nitrification capacity compared to the amount that we could have, or the capacity that we could have at a pH of 7 or 7.5. That means that we will be able to oxidize only 60% of the ammonium that we have present. It can get even lower, around 40%, if the pH approaches 6. So if there is not enough alkalinity because of the high presence of ammonium, free and saline ammonia, in the fecal sludge, the possibilities or the likelihood to have a drop in pH can be very high. If we plot in the effective plan that we have presented before, the effect of the discharge of the fecal sludge in the system, but now attending at the alkalinity consumed and the pH that we will likely generate in the, or have experienced in the aeration tank, we can see that with already 4% discharge of fecal sludge, the pH in the system will drop or approach 5. And values as low as 6.2, 6.3 can be found at around 2.5% fecal sludge discharge. So values as low as 2% will already cause a drop in the alkalinity consumption in the plant and lead to pH values lower than 7. If, in addition to that lower strength or the discharge of lower strength fecal sludge, we look at what happens when we have high strength fecal sludge, a similar profile can be observed, where already the pH can drop below 6 and approach 5 when only 1% of fecal sludge is discharged into the activated sludge plant. So basically, the risk to have a drop in pH, regardless the type of fecal sludge that we co-treat or we try to co-treat, are very high in that system. What happens with the quality of the effluent? As we discussed before, the soluble unbiodegradable organics will have the strongest impact on the effluent quality, particularly because they cannot be removed by physical means and they cannot be removed either by biological means. What implies that they will have or will define the minimum COD effluent that we can have in the plant. Below that value will be very difficult to go because of the nature of these components or these fractions. Pondering or weighing the concentrations of unbiodegradable soluble organics for the fecal sludge and for the wastewater, we can estimate what is the minimum COD that we can observe in the effluent, and that can be quantified with this expression. And in a similar way, we can obtain a similar an expression to quantify the total nitrogen concentration in the effluent with this equation. And as observed, also the COD in the effluent will increase considerably as the fecal sludge discharge increases. And already for some values, we'll reach concentrations of 200, 300, 500 milligrams per liter of COD with less than 1 or 2% discharge of fecal sludge. For total nitrogen in the effluent, we can observe a very similar trend when less than 2% can lead to more than 20, 30 milligrams per liter of total nitrogen, and that will logically exceed most of the standards that have been proposed for the discharge of nitrogen compounds in treated effluents. Regarding the total solids concentration in the effluent, because of the very high accumulation of solids, the possibilities to have a high concentration of solids also leaving the treated effluent are higher and will likely reach more than 30, 40, up to 50 milligrams per liter with concentrations of 4 to 2% fecal sludge. In addition to this, you can say, okay, maybe another option is to try to make the secondary settling tanks larger to be able to cope with the increase in solids concentration. That can be computed based on this equation modified from Ekama and Moraya, published in 2004, where we take into account the amount of wastewater treated, of fecal sludge treated, and the expected total solids concentration in the activated sludge tank. Even for values where the settleability of the sludge used to be very good before the disposal or the discharge of fecal sludge, we can see that the increase in the required area of the secondary settling tank can be dramatically higher. For example, in less than 2% fecal sludge, we will already need like 25% more area for the lowest strength digested fecal sludge, but we may even need to double the area of the secondary settling tank if stronger fecal sludges are treated. So any discharge of fecal sludge, because of the high accumulation of solids, will imply that the area required for the secondary settling tanks needs to be increased considerably. And in most of the cases, these characteristics cannot be foreseen by a designer, and very likely, if the plant is already built and fecal sludge starts to be discharged, very likely the plant will be affected by some or most of these factors. And you can say, or could ask, what about anaerobic treatment of fecal sludge? What about to treat it anaerobically? Under which circumstances does it make sense? Is it suitable? Similar to aerobic treatment, we can also assess the effects of the discharge of fecal sludge on the plant. And in this case, based on design criteria, we need to look at the organic loading rate. If the plant, or if a plant, fictive plant, is designed for 3 kilograms of COD per cubic meter per day, only with the discharge of fecal sludge, it will be a serious and considerable increase of almost double regarding the organic loading rate, with less than 1 or 2% fecal sludge discharge. What are the implications? Well, if we try to express it in terms of solid loading rate, the solid loading rate will increase also considerably, between 1 or 2 kilograms per cubic meter per day, with regard to the original 0.25 kilograms of design for this fictive plant, what means that the concentrations will maybe triple or increase by about 5 times. If the plant is not designed to cope with this increase in solids, very likely will not have enough time for the anaerobic digestion of these solids. And one of the factors that can exemplify this effect will be, for example, the drop in the SRT, in the solid retention time. If the solid retention time is about 10 days for a system where no fecal sludge is treated, it will decrease to less than 8 days when the fecal sludge starts to be disposed of or treated, co-treated in this plant. That will already impose a limitation, implying that the system may be short in about 20% in total volume required for the anaerobic treatment of this fecal sludge. So, overall, the maximum fecal sludge volume that we could co-treat in the plant will be basically limited or depend on the maximum amount of solids that can be treated or accepted in that or in those plants. For most of the plants, for example, for the aerobic plants, preferably the total concentration should be lower than 6 grams per liter. But as we already saw, with 1 or 2% discharge of fecal sludge with regard to the total influent treated, this concentration can be very easily exceeded. Regarding the aeration and capacity and efficiency, there should be sufficient capacity installed to cover the new oxygen requirements and to cope with the decrease in the aeration efficiency. What also means that for already 1 or 2% fecal sludge discharge, these capacities may need to be doubled or tripled or 2 or 3 times higher in that system. Another point or aspect of that needs to be carefully assessed is the availability of alkalinity in the system. If the alkalinity drops below 15 milligrams per liter of alkalinity in that plant, then the risks to have a pH lower than 7 or 6.5 will be much higher, and very likely the wastewater treatment plant will suffer of a tremendous instability, first for nitrification and possibly also for the removal of the organics. What about other processes? Well, for example, the area of the secondary setting tank has to be big enough or large enough to be able to handle the increase in solids. What needs to also be foreseen by a designer, and in most of the cases this is not a common practice, the effluent standards will be likely exceeded because the fractions or the concentrations of unbiodegradable soluble components, either organic or nitrogenous of nitrogen origin, will be much higher, and because they cannot be removed, they will have the strongest impact on the effluent standards. So possibly, to meet the effluent or to comply with the effluent standards will be one of the biggest limitations for the plant. And like for aerobic systems, there is the strong need to have enough spare capacity to be able to provide enough retention in the anaerobic systems to degrade all the fecal sludge discharged into the plant. So, based on all these concepts, what we can say is that if the plant is not built ex professo or upfront for the treatment of fecal sludge, either under aerobic or anaerobic means, the risk to have a plant that goes out of stability or becomes overloaded are very high. So to co-treat the fecal sludge in an existing plant may not be the best choice. On the other way around, if the plant is going to be designed for the co-treatment of fecal sludge, very likely the system needs to be very large and robust, more robust than usual to treat wastewater because of the particular nature of the fecal sludge. And possibly it will not be cost effective or it will not be worthwhile because the amount of organics that can be really biodegraded compared to the total concentration of organics or nitrogen is very low, of only 25 to 50%. So possibly it will not be a good decision to co-treat this fecal sludge in an existing plant or in a plant to build. There will be a lot of effort, there will be a lot of infrastructure needed for the co-treatment, and in the end it will be mostly transfer of solids from one point to another with a very little added value. So overall, these conditions need to be carefully assessed and evaluated in an existing plant or to build a new one, and considered always against other potential ways to co-treat these activities, these fecal sludge in a more efficient way and maybe even more cost effective. Thank you very much. Have a good day.